find the length or arc length of the function y equal to the integral from 0 to x of the square root of, I've decided on t squared plus 6t plus 8 dt. And where x is between 0 and 4. Now, I will point, I should change my, I need to fix my video setting here. 1 second. I do like the 3 plus 2 equals, I'm not sure who that is because I can't see the name, but I like your picture. It's pretty great. In my video, there we go. Jackson, I like the picture. It's excellent. So we are looking at this problem. We want to find the length. I want to fix my lights. Sure. Okay. I want to find the length of y equal to the integral from 0 to x of the square root of t squared plus 6t plus 8 dt, where x is between 0 and 4. And the thing I'll say about this problem first and foremost is this problem is designed so that it's actually not terrible. Like whoever wrote this problem was thinking, I know what I'm going to make this problem easy. I'm going to make it so the numbers don't suck. Specifically so that when you take the derivative or the square root of the 1 plus the derivative squared, it comes out nice. That is really why someone has written this kind of awful looking problem. So remember, if we're trying to find the arc length, we're finding the integral from x equals 0 to x equals 4 of the square root of 1 plus the derivative of the function squared. That's what our job is to find. And so what we have to do before we kind of get too deep into this is actually find that derivative. Now here's the thing. We know how to find the derivative of the integral. That's the fundamental theorem of calculus. So we can say right off the bat here that dy dx is equal to the function inside with x's instead of t's. So instead of the square root of t squared plus 6t plus 8, it's going to be the square root of x squared plus 6x plus 8. And then when I square that, right, they specifically made it so the derivative is the square root of something. So then when you square it here, it's just going to be the nice something. And then when you add 1, it's probably going to work out pretty nice. So here's what we're going to get. We're going to get the integral from 0 to 4 of the square root of, that's an interesting question. I had an interesting idea about, I might save this question until later for a thing. The square root of 1 plus x squared plus 6x plus 8, right? Because it's this squared. So I'm going to write that as x squared plus 6x plus 8 plus 1 or plus 9, right? So that's going to be the square root of x squared plus 6x plus 9. Again, I just squared this and added 1 to it. But now, by design, the thing you end up getting after you add the 1 is something that simplifies nicely. X squared plus 6x plus 9 is x plus 3 quantity squared. So I can totally write this as the integral from 0 to 4 of the square root of x plus 3 quantity squared dx. Now, there is one thing to say about this that's usually not going to come up, but I feel like I have to mention it. Technically, the square root of x plus 3 squared is the absolute value of x plus 3. So this is the integral from 0 to 4 of the absolute value of x plus 3. And that's true whenever you take the square root of something squared. It's not really just the something, it's the absolute value of the something. In this case, it doesn't matter because whether x is anywhere between 0 and 4, x plus 3 is still positive. If the limits of integration went further negative, like if we got past -3, then we would have to be concerned about, oh, sometimes the absolute value of that, the insides are actually negative, so we have to do some manipulation. But here, since this stuff is always positive in these limits of integration, we can just drop the absolute values. And most of the time, the problem's going to be designed so that whatever you've got here is always positive, so you don't have to worry about this absolute value garbage, but it is something that actually does matter on occasion. So then we integrate. We get x squared over 4, sorry, x squared over what? I was thinking about plugging in the 4 already. x squared over 2 plus 3x evaluated between 0 and 4. We plug in 4 and we get 16 over 2, which is 8, plus 3 times 4, which is 12, minus we plug in 0 and we get 0 plus 0. So we get 8 plus 12, which is 20. So that's how you tackle a problem like this. You're like, oh, I'm really just finding the, right, it's designed so that when you do the arc length formula, it comes out really, really nice. So you can kind of make up just about any, well, maybe not just about, I tried making up one, it did not come out so well. So you could say, I want to find the arc length of y equal to the integral from 0 to x of the square root of kind of, you could pick a lot of things. Maybe not a lot of things, but a number of things. One thing you definitely pick is a sine or a cosine function. So maybe I'm going to make it, let's make it, be a little bit careful. Sure. Let's make it, I think I wrote one down here. Oh yeah, I did. I totally did. I'm smart sometimes. Sine of t over 3, where x is between, I guess it's 0 and pi. Again, this is the same idea as the last one. We know we're going to use the arc length formula. So I'm going to do the integral of the square root. Well, actually, really, I know I'm going to do the integral of ds. This is really what I am thinking of when I'm finding the arc length. But then I know that ds is the square root of 1 plus the derivative, either dy dx or dx dy, right? You can take the derivative of y as a function of x like we have here, but you can also take the derivative of x as a function of y, depending on what the setup is. So it's dy dx, quantity squared, dx from x equals 0 to x equals pi. We just need to know what that derivative is. Well, we can find that right here. The derivative is not hard, right? It is specifically designed to be straightforward if you know the fundamental theorem of calculus. So the derivative of this integral is just the square root of sine of x over 3. So then we jam that in there. So then look what I've got. I've got the integral from 0 to pi of the square root of 1 plus the square root of sine squared is just sine. Ooh, did I make a mistake? I think I did make a mistake. That's interesting. I feel like let me double check something real quick because I feel like this maybe I'm thinking of this one. Ooh, yeah. Okay, so I will fully admit I might have thought this one was a little easier than I thought it was going to be. That's all right. It happens sometimes. Here's what I thought was going to happen. Yeah, that's wrong. That's real wrong. Here's what I really thought. Oh yeah. Okay. So still going to go with x over 3, even though it's not excellent. Not really a pun, but kind of intended. I thought what was going to happen. I was not thinking fully. I thought I was thinking sine squared, and then I really thought I was going to have like 1 minus sine squared, which is going to be cosine squared. Okay, so this problem, which is similar to problem 42, is a little bit less nice than I thought it was going to be, but we still have an idea of where it's going to go. So the square root of this squared is sine of x over 3. Oh, yeah, I don't want sine. Okay, it really does need to be cosine for this to actually work. So let me change it to cosine. Sorry about that. I thought something else was going to happen. So we want to find that instead. Now, I will tell you right now, the problem that's actually on the homework, which is cosine of 2x, is a little bit nicer than this is going to be. But the idea is still going to be the same. This idea is, I'm not going to lie, one that I have struggled in the past with to wrap my head around exactly. I mean, not wrap my head around, but to kind of see the intuition to say, how do you know what to do next? Yeah, how do you know what to do next? Here's the only way I really know how to say it. I'll go back to it. So yeah, all right. I'm fully admitting this problem is harder than I thought it was, but definitely not impossible. So here's the thing we need to know. We need a trig identity, and it's kind of So we have some half angle identities that say, how do I like to write them? I usually write them this way. Cosine squared of an angle is equal to 1 plus cosine of twice the angle over 2. And there's also a sine one. There's sine squared of an angle equals 1 minus cosine of twice that angle over 2. You might have learned alternate versions of these, which is perfectly fine. You might have learned it as, or you might never have learned it. You might have learned it as cosine of theta equals plus or minus the square root of 1 plus cosine of 2 theta over 2. And similarly, sine of theta equals plus or minus the square root of 1 minus cosine of 2 theta over 2. Yeah. But this version's a little bit nicer, so that's what I'm going to use for now. So here's what I'm seeing. I'm seeing 1 plus, my numbers are probably not going to work out so great. So I'm seeing 1 plus cosine of 2 theta. So 2 theta equals x over 3. Theta equals 1/2 of x over 3, which is x over 6. Okay, so we need to make this look like that. We need to make it look like 1 plus cosine of 2 theta over 2. So say, okay, I've got 1 plus cosine of x over 3, and I'm going to multiply it by 2 over 2. So I really got 2 times 1 plus cosine of x over 3 all over 2. If I'm pretending like x over 3 is equal to twice theta, so that x over 6 is equal to theta, which you won't have to do in this particular version of the problem, but you will have to do this 2 thing here. I can say that this is equal to 2 times 1 plus cosine of 2 theta over 2 is equal to cosine squared of theta. That's kind of funky. So in your problem, where instead of having something dumb like that I made up, like x over 6, right? In the problem that you guys are actually working on in the homework, you get the much nicer 2x here. And so then when you write this, you'll get 2 cosine squared of just x instead of x over 6. But you still have to deal with that 2. So that's what's going back in the square root in our integral. Right? So 1 plus cosine of x over 3 becomes the square root of 2, or I should say the inside become 2 times cosine squared of x over 6. That's a little bit weird. Are there questions about this? Because I feel like there might be questions about this. Okay, here's what I would do next. Square root of 2, so this square root of 2 times cosine squared of x over 6. Square root of 2 is just a, oh, could you explain why I had to multiply by 2? Yes. So I'm trying to get this. Trying to get 1 plus cosine of 2 theta. Or this is what I have, I should say. But this is the trigger. You know what I could have done, which might have made it a little bit easier to see? I could have multiplied both sides of this by 2. I could have said, hey, 2 cosine squared of theta is equal to 1 plus cosine of 2 theta. I could have done it that way. Yeah, I can definitely explain the x over 6. So, right, so here's what I have. I have 1 plus cosine of x over 3. And I know, really from experience, that when you have 1 plus cosine of an angle inside of a square root, there is a tricky way to make that into something with just cosine squared. And the tricky way is using the half angle formula, which is that cosine squared theta equals 1 plus cosine of twice theta over 2. I have this side of it, kind of. I'm trying to make it into that side of it. So I'm trying to take this side and actually make it look like what I have, which is 1 plus cosine of x over 3. So what I'm doing is I'm saying, okay, well, I want this to be x over 3. So if twice theta is x over 3, then theta is half of x over 3, which is just x over 6. And then to get rid of this 2 here, I multiply both sides by 2. But what I really did was I just wrote it as times 2 over 2 to make it, this is kind of the way I've seen it done before, but you're right, really don't do it that way. You can just say, the thing I know here, I'm going to multiply both sides by 2, cancel that with that. So then 1 plus cosine of x over 3 is equal to 2 times cosine squared of x over 6. Which is exactly what we got right there. So hopefully that explains things. Basically, again, the idea is that I know I've got 1 plus cosine of something, and I know there's a way to turn 1 plus cosine of something into cosine squared of something that's slightly different. It's a little bit tricky. Like the first time I saw this, I was like, where did they get that from? I'm like, oh, they got it from the half angle formula. Okay. So that said, we now have this. And you can think of the square root of 2 times cosine squared of x over 6 as the square root of 2 times the square root of cosine squared of x over 6. The square root of 2 is a constant multiple that can come out in front. And then I'm going to be integrating from 0 to pi the square root of cosine squared of x over 6. But the square root of cosine squared is just cosine. Really, it's the absolute value, but we're not going to worry about that. So at least I'm not going to worry about it here. It's cosine of x over 6. You will not have to worry about it in the problem you have, because when you do this problem, your answer will be essentially the same as mine, except instead of having x over 6 here, you're going to have just x. Yeah, because your problem starts off with a 2x and you get x. Yeah. Dx. And since the limits of integration from 0 to pi over 2, which is in the first quadrant, cosine is positive in the first quadrant, so there's no worry about it being negative and having its absolute value garbage. We're almost done, but certainly this is the hard part. It's not hard to take the derivative here, but it's hard once you get to the square root of 1 plus cosine of 2x is what you will have in yours, or 2x. So your 1 plus cosine of 2x, it'll turn into 2 times cosine squared of just x when you do this problem number 42. It's a tricky problem. And then finally, we integrate this, which is not so tricky. So the integral of cosine of x is just sine of x. Ooh, this is actually, I made it a good problem. So this is going to be the square root of 2. I did a good job. The integral of cosine of x over 6 is sine of x over 6. But there's something I'm missing. There's a factor I'm missing here. What else do I need to, I usually think of it as dividing. What do I need to divide by? You're very close. I actually need to multiply by 6 or divide by 1/6. Because so let me explain just in case you've forgotten the many u substitutions. If you took the derivative of sine of x over 6, that derivative would make you multiply by 1/6. So we need to divide by 1/6 to account for that eventual multiplication by 1/6. So that's from 0 to pi. So we end up with, I'm going to multiply by 6. So I get 6 root 2 times sine of pi over 6 minus sine of 0 over 6. Sine of pi over 6 is 1/2. Sine of 0 is 0. So I get 6 root 2 times 1/2, which is 3 root 2. That's a tricky problem. Definitely the hard part is dealing with the 1 plus cosine of an angle transforming into 2 times cosine squared of half that angle.
So I guess actually let me write that down on the other side, because I think that's kind of the that is kind of the real important part there. Oops, let me do that. So if you're trying to integrate, yeah, I'm gonna erase this. So if you're trying to get to a place where you're integrating the square root of 1 plus cosine of an angle, all right, theta is x, it's going to end up equaling the integral of the square root of 2 times cosine squared of half that angle. Yeah, that's not the worst thing I've ever seen, but I've seen a lot of terrible stuff. So okay, I mean mathematically, like not in real life. Yeah, good. So good question. All right, let's see. Should we do 1 or 2 more arc length problems? So let's do 1 or 2 more arc length questions. Maybe we'll talk about surface area for a second, and then some people ask for some review stuff as well. So we should then we'll go back and we'll review a little bit. I suppose I can look at the other problems that were asked about. So for those of you just joining us, we just did a problem similar to problem 42 in the web work stuff. Yeah, we can look at that one. Sure. Yeah, so I would say just looking at these problems, problem 39, 40, and 42 all have the same sort of process where you have to do the fundamental theorem of calculus to do like the arc length. But problems 38 and 41 look a little bit different. So let's look at 41, and I'll even not change the numbers just to be super exciting. So problem 41 from the one word. So again, we're asked to find the arc length. So length of y equal to 1 over root 3 times the square root of 1 minus 3y squared. Okay. And so I don't see anything obvious that's going to happen here. And also the limits of integration are 0.05 to which seem really dumb. Although I can see it's right, if y got too big, then we would no longer be in the domain of this function. So I guess it makes sense that they're kind of small. All right, so if I'm doing an arc length question, I'm going to do the derivative and square it before I kind of write the integral. So let's find dy dx. So this is 1 over root 3 times 1 minus 3y squared to the 1/2 power. So that's going to be the constant 1 over root 3 times the derivative of stuff to the 1/2 power is 1/2 times my stuff to the negative 1/2 power times the derivative of that stuff, which is going to be negative 6y. And it's really going to be in my interest to simplify this before I start squaring it out. So 6 divided by 2 is 3. And 3 divided by the square root of 3 is the square root of 3. So I would really much rather write this as negative square root of 3 times y over 1 minus 3, or the square root of 1 minus 3y squared. Right? That's what being to the negative 1/2 power means. It means it's over the 1/2 power, which is over the square root. And I like to write it with square roots because that makes it really, really obvious to me that if I square it, they're going to get nicer. So if I look at dy dx quantity squared, I'm hopeful. Because when I square this, the top squared is just 3y squared, and the bottom squared is 1 minus 3y squared. Oh yeah, I did this problem with someone else, I think, or a similar problem anyway. This one ends interestingly. It actually ends with, so I guess we'll have to figure out how the end works. So then we're going to throw this into the formula, right? That the arc length is the integral from 0.05 to 0.1. The numbers are almost never nice, of the square root of 1 plus this derivative squared. So it's the square root of 1 plus 3y squared over 1 minus 3y squared. And definitely I should get a common denominator. So the negatives stay? No, because it's squared stuff. It's a good question, right? That squared means we get rid of the negative. But yeah, excellent question. So I'm going to replace this 1 with 1 minus 3y squared over 1 minus 3y squared. And now I can add those together. And look what I get. I get the integral from 0.05 to 0.1 of the square root of 1 minus 3y squared plus 3y squared is just 1. And this happens a lot. Like these arc length problems, maybe the limits of integration are terrible numbers, but usually they're designed in such a way that they actually simplify to something you can integrate. So I get the square root of 1 over 1 minus 3y squared dy. Okay, let's do that on the other side. Because this is where I have to remember how to do it. Or one of you has to remind me how to do it. So I've got the integral from 0.05 to 0.1 of 1. Oh, sorry. So I should point out the square root of 1 over 1 minus 3y squared is just 1 over the square root of 1 minus 3y squared. You know what that looks a lot like to me? It looks a lot like I'm going to ignore that 3 for a second and say, oh, well, I know how to integrate the square root. I know how to integrate 1 over the square root of 1 minus y squared. I know the integral of 1 over the square root of 1 minus y squared is just the arc sine of y, or if you prefer, the inverse sine of y. And I will fully admit, I always struggle. Oh, I guess we could do it that way. Okay, yeah. I do struggle with remembering how to make this turn out how it's supposed to. But I guess I should show you how to do it, right? Because you might not remember it either. So just want to make sure I'm not missing something. No, I don't think I am. I was kind of hoping there would be an extra square root of 3 somewhere hanging around. I guess not. No, I guess not. Okay, we're not so lucky. So here's one way to do it. If you recognize, oh, this looks like it's going to be kind of like an arc sine thing, here's what you want to do. If you don't remember, like there's a formula for 1 minus ax squared here. I don't remember what it is. Like I know there's probably a dividing by a square root of 3 somehow. I don't remember. So here's what I do. So I want to have the square root of 1 minus, I would love to have the square root of like 1 minus x squared. So I'm going to rewrite 3y squared as some quantity squared. 3y squared is actually the quantity, the square root of 3 times y squared. Right? Right. And I'm going to choose this to be my u. So that u is equal to the square root of 3 times y. And that du is equal to the square root of 3 dy. Or du divided by the square root of 3 is equal to just dy. So here's how I'm going to rewrite my equation. This here, instead of being 3y squared, is now going to be u squared. Let's do it the other color. And this dy, instead of being dy, is going to be du over root 3. And you know what? Now I can totally integrate it. And you know what? I probably also wouldn't bother worrying about the limits of integration. I wouldn't change them. I would just leave them as y's for a minute. Because I'm just going to change back. Usually I would change them, but here that feels like we've done enough. So we're going to integrate this. This is going to be the arc sine of u, or the inverse sine of u. So it's going to be 1 over root 3 times the arc sine of u, evaluating between these two things. Y equals 0.05, y equals 0.1. And then finally, we're going to plug back in that u is equal to root 3 times y. So we actually end up getting 1 over root 3 times the arc sine of root 3 times y from 0.05 to 0.1. So then we throw this into the formula and we get, this is terrible. We get 1 over root 3 arc sine of root 3 times 0.1 or root 3 times 1/10. I would probably write it as root 3 over 10 minus 1 over root 3 arc sine of root 3 times 0.05. 0.05 is 1/20th. So root 3 times 1/20th is root 3 over 20. And that is a terrible looking quantity, but that is our answer. So yeah, I guess the formula, that's terrible. Right? Yeah. So just so you guys know, actually, so I know really, I guess the formula for the integral of 1 over the square root of 1 minus something times x squared, like ax squared, there's probably a formula for this in your book somewhere. Apparently it is 1 over the square root of a times the arc sine of the square root of a times x. Good to know. All right, so arc length, kind of terrible. It does come. Let me do, yeah, we got time. I'm gonna do one more arc length example, and then I'm going to, what am I gonna do? I'm going to merge that example into there's a word I'm looking for, into a surface area example. It's kind of crazy. Here's the thing, arc length and surface area, very, very much related. Then after that, I will try and backtrack a little bit. So let us talk about this one. Yeah, sure. Those numbers are awful. So I'm gonna look at this one from, this is similar to problem 38, not exactly. So I want to find the length of, do I really want to do this then? Sure, why not? X equals y cubed over 6 plus 1 over 2y. But I'm going to pick different limits of integration because those just look heinous. I'm just going to pick something easy like y goes from 1 to 3. Sure, why not? Notice y couldn't go from 0 to anything because 0 is not in the domain of this expression. First thing I want to point out about this problem, it has the hallmark look of the kind of problem where after we differentiate this and square it and add 1, well, I should say, after we differentiate this and square it, we're going to get a minus 1/2 of the middle. We're going to add 1. We're going to get a plus 1/2 of the middle. We're going to factor it back out because you just changed the middle sign of the thing. Then the square root of that will be something nice. It'll actually be the derivative of this, but the opposite sign. And then when you anti-differentiate, you're going to do all this work. It's going to be a big old circle. And you're going to get back to the antiderivative is going to be this function, except it's going to be y cubed over 6 minus 1 over 2y. And you should, when you see something that looks like, oh, I've kind of got this thing plus this other thing, they're very kind of separate. You should be thinking, oh, it's that thing where when I do all the work, I get the minus 1/2, and then everything works out, and I essentially end up with almost the same thing I started with. That is what you should be thinking when you see this kind of problem. Okay, so let's do it relatively quickly. So x prime or dx dy is the derivative of this, which is 3. Oh yeah, that actually brings up a good point. You don't have to use the quotient rule here, right? And I know it's been a while since you probably have it. I just want to point out, for the derivative of y cubed over 6, it's just 1/6 y cubed. So the derivative is 1/6 times 3y squared. Just want to make sure everyone's okay with that. For 1 over 2y, we don't have to use the quotient rule either. We should really be thinking of this as, right, this is 1/6 y cubed. This is 1/2 times y to the negative first. And this derivative is going to be minus 1/2 y to the negative second. And I've kind of scrunched things in there. Oh well. Okay. And then dx dy squared is going to be, well, I'm going to simplify this. This is 1/2 y squared, or y squared over 2. And this is minus 1 over 2y squared. And I can definitely see that for the middle terms, when I multiply these together, that this y squared and the y squared in the denominator are going to kind of cancel each other out. So I'm going to get a constant term, and I would bet my life it's going to be negative 1/2. Maybe not my life really, but I know it's going to be negative 1/2. So. Anyway, so we're going to square this. And you can either FOIL it out, or you can just do like, I know when I square a binomial thing, a 2-term thing, it's the first term squared plus 2 times the first term times the second term plus the second term squared. So it's going to be the first term squared, which will be y to the 4th over 4 plus 2 times the first term, which is y squared over 2, times the second term, which is negative 1 over 2y squared. The negative is certainly important there. Plus the second term squared, which is going to be 1 over 4y to the 4th. And yes, it is plus. And then notice this middle term, those two cancel, the y squared and the y squared cancel, you get negative 1/2. So then we try and write the derivative, or sorry, the arc length formula. The arc length is going to be the integral from 1 to 3 of the square root of 1 plus dx dy quantity squared dy. And we know that here's dx dy squared. It's y to the 4th over 4 minus 1/2 plus 1 over 4y to the 4th. So then when we add 1 to it, 1 plus negative 1/2 is positive 1/2. So this ends up being exactly the integral from 1 to 3 of the square root of y to the 4th over 4 plus 1/2 plus 1 over 4y to the 4th. And here's the thing. We know that this squared out gives you this whole thing. And if you change the sign here, or if you make this a plus instead of a minus, you get the same thing. You get the first thing squared plus 2 times the first thing times the second thing. But now the second thing isn't negative. So this sign just changes, right? This changes right there, plus the second thing squared. But that is exactly what's in there. So we know that that thing in there is just y squared over 2 plus 1 over 2y squared, quantity squared. So this ends up being the integral from 1 to 3. Well, the square root of this thing squared is just this stuff inside. Of course, with the plus sign right now, with the minus sign. So I end up with the integral of y squared over 2 plus 1 over 2y squared. But then look, I got this by taking the derivative of this. So I can get the thing with the opposite sign by just changing the sign there. You could also just do the integral, right? But I'm going to get the integral of y squared over 2 is y cubed over 6. And the integral of 1 over 2y squared is going to be negative 1 over 2y. Right? Because it's really 1/2 y to the negative second. You add 1 to the power, you get 1/2 y to the negative 1 divided by negative 1 makes it a negative 1/2. 1 over 2y, I should say, or 1/2 y to the negative first. From 1 to 3. Okay, I'm not going to plug in limits of integration because I've run out of room and it's not that important. The important part is seeing how this works. So many of these arc length problems work this way. Okay. Let me give you a very brief, so I'm going to use the same function, but now we're going to talk about surface area for just one example. And then next week, we'll talk more about surface area. And probably work too, unless you guys don't do work, but I feel like you must, so yeah. Work is force times distance. All right, so surface area. Here's the idea. You're taking some curve. I'm going to draw it like this. From between 1 and 3, right? From 1 to 3. And you're revolving it around some axis. And we'll talk about the axis in a second here. And then we're going to do both. But the idea is, so let's say we go around the, what's the more complicated way? I'm trying to think about what's the less terrible way of doing this. In terms of y. Yeah, okay, sure. Let's go around the x-axis first. So the idea is I'm going to rotate this around the x-axis, and I want to find the surface area of essentially the shell of the volume of the thing, right? So you can either think of it, some people like to think of it as you just get this part revolved around, which gives you like the shell, or some people like to think about it as you revolve the whole surface or the whole region around, and then you get the outer shell of that solid.
It doesn't really matter how you think of it as long as it works for you. And unfortunately, unlike last time where someone had the brilliant suggestion to say that my shape looked like a fancy glass, which I still am in love with, thank you. Whoever said that, it's one of my favorite things that I've had happen all quarter. This is not a very useful fancy glass because the bottom of it would be open. So, right. Oh, well. Maybe like it's a little candle votive holder thing. You put this around the candle and then the candle sticks out of the end, right? They make those things, sure. Okay. So the idea is we're going to take some small section of the arc length. So I'm going to call it ds, and we're going to look at that slice revolved around, which I think of as looking like a rubber band. There's my rubber band. And I'm trying to find the surface area of my rubber band. So I want to find the surface area of my rubber band. So just like, what would you call that? I guess it's like the outer part of kind of a disc. Essentially, I'm taking the circumference of the disc multiplied by the thickness. But this is where things get a little bit wonky. The thickness isn't dx or dy, the thickness is ds. Because there's a little bit of, it's not just straight horizontal or straight vertical, it's curved kind of. So the surface area here is 2 pi times the radius of this times ds. And here's where things get a little bit weird. Okay, so like you've been saying that all quarter long. Yes, things are just weird in counting. So this is my radius of my band. And if I'm going around the x-axis, the radius is how far away I am from the x-axis, which is x or y. Which variable tells me how far I am away from the x-axis? X or y? Oh, that's a good question, James. I didn't think about that. Let me draw a point for you guys. If I say at the point like, 1, 6, am I 1 away from the x-axis or am I 6 away from the x-axis? I see various opinions. So let me make sure the axis, right, here's the x-axis, here's the y-axis. I am definitely 6 away from the x-axis. And I'm definitely 1 away from the y-axis. So here's the thing. The other variable tells you how far away you are from the axis. So the y variable or the y coordinate tells you how far you are from the x-axis. And the x coordinate or the x variable tells you how far you are from the y-axis, right? If I've gone over x, that tells me how far I am from this axis. This axis is x equals 0. It's the y-axis, but it's x equals 0. So if I go over this one, if I go over 1, I've gone from x equals 0 to x equals 1. I am 1 away from the y-axis, which is the line x equals 0. Just like if I'm up here at 6, I am 6 away from the x-axis, which is the line y equals 0. Okay, so here, and this is really super important, the radius is y. I am y away from the axis of rotation. So this is where things get extra, this is where things get even weirder. So in this case, we can write that our surface area is equal to 2 pi times y times ds, where ds is 1 plus dx dy squared dy. So for this particular problem, we can say, the total surface area, right? We're going to add up all the areas of the rubber bands by integrating, just like every other time we add something up. You're going to get the integral from 1 to 3, because I said it was from 1 to 3, of this quantity, 2 pi times y times this ds here, which we did before, right? That's just this here. There's your ds. Also, I saw there was a problem on the homework
where they ask you to find like ds, and if you have, make sure that when you do that problem in homework and you write what ds is, you include the dy or the dx at the end. You have to have that to make it right. So here ds is y squared over 2 plus 1 over 2y squared dy. So then before you can integrate this, in parentheses too. So then before you can integrate this, you have to distribute this y. So we're going to be integrating, and I'm not going to finish the integral because I don't think that's the important part today. I'm going to bring out the 2 pi, make the integral from 1 to 3 of y times y squared is y cubed over 2, and y times 1 over 2y squared is 1 over 2y. So you'd have to integrate this. You get y to the 4th over 8 plus 1/2 natural log of absolute value of y. Okay, the thing I need to impart to you is that things are different if we go around the x-axis, but not that different. Yeah, I'll say that. Sorry, I don't actually want to erase you. You're the only thing I didn't want to erase. Maybe not you either. We'll see. Okay, so what was the function? It was 1 over 2y. Yeah, okay. So here's the thing. If instead we go around the x-axis, so again, I'm looking at, a region that kind of looks like, I don't really know what this arc length actually looks like. I'm just drawing it like it's something. From 1 to 3. If I go around the x-axis instead, if I go around the y-axis instead, it's going to look kind of like this. Again, a not very useful container that's got an empty bottom. But again, it's the same idea, right? I'm going to take this little small section of ds here, and I'm going to revolve it around the y-axis to get another rubber band looking shape. And now, right, that rubber band, the surface area of this rubber band is once again 2 pi r ds. Circumference, 2 pi r ds, thickness. Okay, but now, this time, what's the radius? Last time, when I went around the x-axis, the radius was y. So what's the radius going to be this time if I'm going around the y-axis? Yes, thank you, it's x. Okay, but here's the problem with x in this particular situation. If I'm going to try and find the integral, I've still got ds in terms of y, right? If I was going to find the total surface area, I'm going to do the integral of 2 pi r ds from, I still think I'm going to go from 1 to 3. So I'm going to do the integral 2 pi. I'm going to figure out r in a second. My ds is still, I know I erased it. My ds is still y squared over 2 plus 1 over 2y squared. Right, that's what it was last time? Yeah, that's what it was last time. That was my ds. Okay, here's the problem. Even if I wanted to, I couldn't do this in terms of x. There's no way we're solving this equation for y. Like, I think it's literally impossible to isolate y here. So, well, shoot, our radius is y. Sorry, x. Sorry, x. You guys said x, I said x. Everybody said x. Our radius is x here. Yeah, that's fine. x equals y cubed over 6 plus 1 over 2y. So that's our radius. So if your radius is the variable you're not actually doing things in terms of, you say, oh, I have an equation for that. And you replace it with the thing it's actually equal to. So here's what happens. If you're going around the y-axis, your radius is either x, if you're doing things in terms of x, or your radius is the function that x is equal to if you're doing things in terms of the variable y. And then on the other side, if you're going around the x-axis, your radius is either y, or your radius is the function that y is equal to because you're doing things in terms of x. So right, if instead this function was like, if I was going to like totally change it and say, this function was like y equal to the square root of x, and I was going around the x-axis, then my surface area would be the integral from wherever to wherever of my radius, which is y, which is the square root of x, times the ds part, which would be the square root of 1 plus the derivative of the square root of x squared dx, and then there'd be a 2pi as well. So these surface area ones, there's almost always like a couple different ways you could do it, and it always feels kind of weird. But just remember, for surface area, it's 2pi times the radius times ds. ds is always the same formula it always is, either in terms of x or in terms of y. The radius depends on the axis you're going around. If you're going around the x-axis, your radius is y, or the function y is equal to. If you're going around the y-axis, your radius is x, or the function x is equal to. Okay. So I know that soaked up a lot of the time, but that's okay. I'm gonna backtrack now for the people who have requested more of a review kind of deal. So I'm gonna work on some of these problems for you guys, but I'm going to, actually, let me go back. So here is a link to a review that Grant has posted. And if we go back to his webpage, just so you can see what I'm actually working from. There's also solutions posted. So we definitely won't get through all those right now in the next 26 minutes. But if you look down at the bottom of Grant's resource page, whoops, one sec. Okay, if you look at the bottom here, you can definitely find the midterm one review and the midterm one review solutions, which I think are pretty apt problems. That said, for those of you that have a test coming up, if you have questions and you want to ask me that we don't get to today, we're more than welcome to post a discussion in Canvas, and then everyone can talk to each other about the problem that you have a question about, because I bet everybody has the same questions. Or if you don't feel like being that public, I guess you could email me. And then maybe I'll post it in the discussion in Canvas, and I will remove your name if you don't want me to put your name. But it's good to share your questions, because really, if you have a question, like, you wouldn't believe how many times I get the same question from lots of people, which is really fine. Like, I'm happy to get the same question from you guys, but you could save yourself some effort if you wrote it in the discussion in Canvas, because then you'd be like, oh yeah, I had that question too. Now I can see what's going on with that. But really, lots of you all have the same questions, and you could be helping each other by asking them in a more public forum. I know it can be a little intimidating, but it's just us. We like each other, right? I mean, maybe you don't, I don't know. I like to think you like each other. All right, enough of me blathering on here. Let me get to the point. Where is the point? I lost the point because I clicked away. Sorry, let me go back. So here is this review. And so this is just, a bunch of problems where you're probably gonna have to do some U substitution. So something like, and so again, to me it's hard to want to do these problems because they feel like they're just screaming out the method to be used, but that doesn't mean we shouldn't do them. So here is the first problem. The integral of x cubed over x to the 4th plus 5 quantity squared. And I feel like this is screaming at us that there is an obvious U substitution. U should be the stuff that both is stuck inside the denominator and inside being square, right? It is really stuck inside other functions. And probably more importantly, its derivative is essentially also in the integral. So if u is x to the fourth plus 5, the derivative of u, du dx, is 4x cubed. And I could give not a care or something more forceful about that 4. That 4 is garbage. We care nothing about it except that we have to remember it's there. But it is not important at all. The only thing that's actually important here is that the derivative of this u is something times x cubed, because we need it to be x cubed because we have an x cubed up there. Great. We are super happy about this. This is like the best possible situation. We're going to do whatever you want to do. I personally am going to isolate the x cubed over here and bring the dx over. So I'm going to divide both sides by 4 and multiply both sides by dx, so that I can make the right side of this look like what I actually have in my integral. And again, I'm going to say this every time. When you're doing a substitution, you always want to make sure you deal with the dx part changing into du before you do anything else. That's especially going to be true when we get to problem 4, which maybe I'll do next. So this is my 1/4 du. This is my u. I think it's nice to use different colors when you're changing it to u, because then it's kind of obvious what's what. So this is going to equal the integral of, and you can write this in a lot of different ways. You could write it as 1/4 du over u squared. I would probably jump straight to 1/4 out in front. You can write du over u squared. I would much rather write u to the -2 du, because I know how to antidifferentiate u to the -2, and I have to think about what I'm doing with 1 over u squared. So then we're going to use the reverse power rule, or the anti-power rule. So the antiderivative of u to the -2 is u to the -1st, because we're adding 1 to the power, dividing by the new power. If it's indefinite, which this definitely is, you guys are like, that was lame. I know, but it's still funny. If it's indefinite, you have to go back to the variable you started with, right? So instead of 1/4 u to the -1 over -1, well, first of all, let's pull the -1 out and just make it a -1/4 times, instead of u, it's going to be x to the 4th plus 5 to the -1 plus c. And I would probably leave it like this. You might also write it as -1 over 4 times x to the 4th plus 5 plus c. But that's how that one goes. Ooh, yeah, that next question is good. So ask him if you got them, but I'm going to keep going. Unless you ask me, then I will go back for sure. That's kind of the nice thing about the board. Unless I move really fast, you can usually go back to the question we just did and ask questions about it. As long as I don't get too eraser happy. I would imagine on your, for those of you that are looking for review and have an exam coming up, I'm guessing fairly soon, I will say this, and I said this before, right? At this point, the only methods we have to integrate things are really u substitution or simplify the heck out of it. So this next one is definitely meant to be a trick or a trap or something in between. And it's almost the same. I mean, it's actually not, right? It's very different. The reciprocal of the thing is like not at all the same as the original thing, but it looks similar. And you might get tricked into thinking we could do a u substitution here. Let me point out why we cannot. If we let u equal the same thing, which is definitely the choice that I would make if I was trying to make a u substitution happen, my du would still, let's just cut to the chase. My 1/4 du would still equal x cubed dx. And I want to be extra explicit here. We don't have x cubed times dx. In our integral, we have 1 over x cubed times dx, which is really not at all the same thing. Right? If you want, you could actually write this out more expanded as x to the 4th plus 5 squared times 1 over x cubed times dx. Ho! These things are not the same. Not at all. So we can't do a u sub here. At least we couldn't do it that way. In fact, you can't do a u sub here at all. So the idea here
And this is actually something that we're going to learn is true more generally once we get to, probably once we get to talk about partial fractions in chapter 7, is that when you have a polynomial, I should back up, James. When you have a rational function, which is a polynomial divided by polynomial, if the degree on top is greater than the degree on the bottom, or let's just say greater than or equal to, we probably should just do polynomial division, which means we have to multiply them. So I will fully admit, if this was x to the 4th plus 5 to like the 100th power over x cubed, we'd be done, right? Like there wouldn't be a way to do it really. But this, obviously, the person writing this problem is like, I'm going to make something that makes sense. So we're going to multiply at the top. Multiplying out something squared, you get the first thing squared, so x to the 8th, plus the first thing, or so 2 times the first thing times the, or I'm just using the pattern from before. 2 times x to the 4th times 5 is 10x to the 4th, and 5 squared is 25, all over x cubed. And then I just divide each thing by x cubed, right? X to the 8th divided by x cubed, 10x to the 4th divided by x cubed, 25 divided by x cubed. So I end up with the integral of x to the 5th plus 10x plus 25 over x cubed, which I'm going to write as 25x to the negative 3rd dx. And then we just integrate along our merry way. Integral of x to the 5th is x to the 6th over 6. Integral of 10x is 10x squared over 2, which you really should simplify as 5x squared. Right? Those easy simplifications where you're dividing by 2 or 3 and the thing that's being divided by is a multiple of 2 or 3, like you should definitely do those small simplifications. On the other hand, if it's like 240, 6 over 12, okay, maybe. And then the 25x to the negative 2nd over negative 2. So I'm going to do minus 25x to the negative 2nd. Plus c. Remember your plus c's, they definitely count. And I feel like this next one might not be in our what's the word I'm looking for? I don't know if we've really done a problem like this. So I'm going to start it, but I want someone to tell me if this seems like it's something you haven't done. Still working with the same sort of setup, except now we're going to look at back to more like the first problem, except now instead of x to the 3rd on top, we're going to have an x to the 7th over x to the 4th plus 5 squared again. This one, I will fully admit, is trickier, right? There doesn't feel like there's as much of an obvious choice for you. Because although, well, I will say x to the 4th plus 5 still seems like the choice because it's still stuck. Right, stuck inside a square, it's stuck inside the denominator. But it feels a little less obvious because its derivative, which is 4x cubed, I don't exactly just have x cubed on top. But we can make it work, as Tim Gunn says, make it work. I know it's an old reference. America's, or sorry, not that. America's Next, not America's Next Top Model. The other one, the fashion one. I don't know, what's it called? Anyway, not important. Sorry, I'll think of it. With Heidi Klum and Tim Gunn. And, yeah. Okay. So I'm going to make this choice and I'm going to work on it. I'm going to say, okay, well, du dx is still 4x cubed. And I can still isolate the x cubed because what I can do, even though I don't exactly have x cubed here, I do have enough to have x cubed. Right? I can totally write that as the integral of x to the 4th times x cubed over x to the 4th plus 5 squared dx. So that my 1/4 du equal to x cubed dx, there's still a place for that. That's my 1/4 du right there. And then this thing here, that's still u, but then I have some leftover x's. I have a leftover x to the 4th. And this is what's called a back substitution. So I don't know if you guys have really talked about this or not, but here's the idea. I've got a leftover x to the 4th. Well, I can definitely solve this. So we want to do as little work as possible. You could totally solve this for x and then plug that in for x. But I'm trying to get x to the 4th, and I see an x to the 4th. So I'm just going to say, well, hey, u minus 5 equals x to the 4th. And that's what's going to go in for x to the 4th.
So that's kind of the idea. Often problems like this are set up so that after you deal with the du part first, always with the du part, the leftover x's that you have to back substitute for are kind of nicely, easily solved for over here. So this is going to equal the integral of u minus 5 times 1/4 du all over u squared. The 1/4 can come out in front. And just like in the previous problem where we divided a bunch of stuff by the denominator, we're going to do the same thing here. U divided by u squared is u to the negative 1. 5 divided by u squared is 5 times u to the negative 2. Here's kind of a trick question. What's the integral of u to the negative 1? Kind of just fun to, I spent a lot of time in the mirror, in front of the mirror when I was a kid, doing all kinds of weird things, like trying to raise one eyebrow. I was like this, raise an eyebrow, and practice with the other one like this. So I just kind of like look at myself on camera when you guys are saying anything. The integral of u to the negative 1 is not quite x, or u is what I would say. So if I rewrite u to the negative 1 as 1 over u, that might make you guys think, oh, the antiderivative of 1 over u is the... Anybody there? I memorized there. Yeah, thank you. You guys are awesome. Natural log of the absolute value of u. Perfect. Minus integral here we do. So u to the negative 1 or 1 over u is the one we can't use the power rule, the anti-power rule. Here we see it's 5 u to the negative 1 over negative 1 plus c. So then my final answer would be 1/4 times natural log of the absolute value of x to the 4th plus 5 minus, well, really plus, it's a minus and minus. So minus, which is plus 5 times x to the 4th plus 5 to the negative 1. Plus c. So that's how you do that one. If you're like, I don't really know about this back substitution stuff, it probably means you haven't talked about it in class, and so I wouldn't worry too much about it, but it's not a bad problem. Okay, we've got 11 minutes. We have time for at least 2 problems. Yeah, definitely. So there's some you just have to know, not like this next one, but the one after it. So where'd you go? Integral of e to the root x over root x dx. What do you think I might choose for my u? There is probably more than one possible choice here, but there's one choice. Yeah, exactly. I'm typically trying to pick a thing that isn't like super complicated because its derivative I want to be not terrible. And while you could probably correctly pick e to the root x and have it work out, the more normal, natural choice here is just to pick the root x, because one, it's the thing that's kind of stuck in a place, right? The square root of x is stuck. Well, it's actually stuck in 2 places, right? It's stuck in the denominator and it's stuck in the exponent there. So, okay, that's interesting. We might end up getting e to the u over u. We won't, but we might, and that's why we have to be careful. So our u is the square root of x, which I'm going to rewrite as x to the 1/2. And then our du is 1/2 x to the negative 1/2 dx. And here's the mistake I want to help you avoid. You have to deal with the dx part first. If you start trying to replace things with u, you're going to get e to the u over u, and then you're still going to have dx over here. We really have to make sure you can't just magically say, oh, it's du now. We have to actually say, well, dx is equal to a thing, and it has to get replaced with the thing it is equal to. So let's do that here. So I've got du equal to 1/2. X to the negative 1/2 is 1 over the square root of x dx. I will fully admit, some people really just like to solve for dx. That is never the way I've liked doing it, but I will show you that it works just fine. A lot of the time. I will say it doesn't always work fine. But here you could totally say, oh, dx is equal to 2 root x du. And then you can rewrite that as the integral of e to the root x over root x times 2 root x du. And then before replacing the dx with u's, the square root of x with u's, you can say, oh, that root x and that root x, they cancel out. So you just get e to the u times 2. And that is a perfectly legit and normal way of doing it. It's just not the way I usually do it. I am much more the kind of person that says, okay, I want to make this look like on the right-hand side something I have in there. So I would probably take this and multiply both sides by 2 and say that 2 du equals 1 over root x times dx. Because then I can say that this 1 over root x times dx, that's equal to my 2 du. But really, either way is correct. Whatever way you want to get there is really fine, as long as it works out correctly and the process is correct. So this is going to be the integral of 2 du times e to the u. Okay, the 2 is a constant multiple, it just hangs out. Integral of e to the u is e to the u. Plus c, so then we get 2e to the square root of x plus c. And that's it. All right. Oh yeah, we got so much time. But again, I will say, you really can do it this other way. It is a little bit dicey if things don't cancel out nicely. Like if you plug in dx equal to some stuff, you really need all the x things to cancel out. Otherwise, you're going to have problems. Or to be easily replaced with u. Right? You could have then said, oh, well, root x is just u. So you can say dx is 2u du. And then you could have said this is u, e to the u over u times 2u du, and the u's cancel. Like, as long as you, in fact, let me actually say this really, really strongly. If you're doing a u substitution, you can't have any x's, right? All of the variables have to be u or the same, more specifically, before you can integrate. That d whatever has to be the same as the variable there. You cannot have multiple variables, at least at this stage. Multiple, yeah, that's what I say. Yeah, there's definitely multiple variable integration that happens later, but it's still pretty much obeys the same rules. All right, let's look at least one more. Oh yeah, good times. Integral of 1 over 9x squared plus 4 dx. I'm so not happy about this integral already. So here's what I see. I'm really trying to find a red pen. I want a red pen. I guess I'll settle for a green pen. Okay. What I see here is I see arctangent. I really am ignoring the 9 and the 4 for a second, saying, oh, I'm seeing 1 over x squared plus 1. I know the integral of 1 over x squared plus 1 is arctangent of x. But now I have to adjust for these stupid coefficients. I really hate that 4 there. There's a lot of ways to do this. I wish I could memorize the formula. Like, it does not stick in my head. If you're allowed to use formulas in your textbook, or use formulas in your textbook. But here's what I know I need to do if I don't have any formulas at my command. I need to make it look like the integral of 1 over u squared plus 1. But it really does have to be a 1 there, not a 4. There is definitely a formula for if you have like a squared there, but I don't remember it. So what I'm going to do before I do anything else is I'm going to factor out a 4 from the bottom. So factoring out a 4, this becomes 9/4 x squared, and this becomes 1. And then I can pull that 1/4 out in front. We're going to do arctangent, but the problem is I don't know what is exactly, like, I'm pretty sure it's arctangent of 3/2 x, but there's probably like a factor, like it is arctangent, Morgan. I just don't know what the coefficients exactly turn out to be. And so the way you can always make sure it works is to do a u sub first. And that's what I'm trying to make happen here. So I know it has to be 1 over something squared plus 1. And I feel like the pen is really hard to see right now. Let me use orange instead. So this is, I'm going to bring out the 1/4. And I still have the integral of 1 over 9/4 x squared, which I'm going to write as the quantity 3/2 x squared. Because that's 9/4 x squared. And now I'm going to let u equal that. So u equals 3/2 x du. The derivative of 3/2 x is just 3/2. Du is 3/2 dx. So dx equals 2/3 du. So I'm going to rewrite this in terms of u now. I'm going to get 1/4. 1 over, well, I'm sorry, I should back up. I should do my dx first, right? Let's go out of the device, do dx first. So dx is 2/3 du. It's always easy to make sure the change happens if it's just a constant multiple, right? Here dx is 2/3 du, you just replace it. And then on the bottom, I have 1 over u squared plus 1. I'm going to do two things. I'm going to bring out the 2/3. 1/4 times 2/3 is 2/12, which is 1/6. This is going to be 1/6. And now the integral of 1 over u squared plus 1 is the arctangent of u. Plus c. And then replacing u with 3/2 x, I get the arc, I get 1/6, the arctangent of 3/2 x plus c. There's probably a formula for this somewhere in your book where it's like you've got 1 over ax squared plus b squared, and the formula is like 1 over a times b arctangent of a over b, or I don't know, something crazy like that. I would never be able to memorize that formula, but I definitely know how to make it into something that I do know how to integrate by doing a u substitution. That said, I would definitely recommend, if you're allowed to use a formula with a table of formulas on it for things like arctangent of 1 plus ax squared or ax squared plus a squared or whatever, I would definitely do that. But I will say, like, I think here's what I'm pretty sure is true. I'm pretty sure that most tables for arctangent give you something more like this. They say, oh yeah, the integral of 1 over u squared plus a squared du is equal to the arctangent, I think it's actually, 1 over a times the arctangent of u over a plus c. But, right, if you've got, I guess we could make, yeah, I suppose we could, yeah, that would totally work. So if that was our formula here, we would be like, okay, well, our u has to be 3x and our a is 2. And I'm probably missing something. Now I have to check this out. Let's see, 1 over. Now I feel like, so let me look up the formula just to make sure I've said this right, because I don't want to leave you on the note of, here's the wrong formula for arctangent. So I'm looking in the back of my book, A Brief Table of Integrals. Sorry, don't want to, really would be terrible to leave you with the wrong thing. Where did you go? So, nope, I got it right. Okay, good. I'm not a complete fool. So yeah, so the problem is you kind of have to make your integral look like u squared plus a squared before you can apply the formula. And right here, I didn't have, right, if I let u equal 3x, I have to make sure I change my dx to du. So yeah, you kind of, if that's the formula you've got, you kind of have to do this u substitution.